Welcome to Theory of Computation. This is lecture number 35. In the last lecture, we were discussing the traveling salesman problem. We looked at three different versions of it. The first version was called the general TSP, or just the traveling salesman problem. And that's the problem in which you're given an arbitrary graph which has weights on its edges, and you are asked to find the cheapest Hamiltonian cycle in that graph. And the weight function does not satisfy any constraints other than the fact that the weights are non-negative or they are positive integers. So you can have any arbitrary graph. This is the general TSP. After that, we looked at a restricted version of the traveling salesman problem, and that was the metric TSP. In this case, you're given a complete graph. So the underlying graph is extremely simple. It's a complete graph. Every vertex is connected to every vertex, and the edges have weights on them. Furthermore, the edges satisfy the triangular inequality. What does the triangular inequality say? Well, it simply says that if you go from a vertex A to B and then to C, that would cost you at least as much as if you were to go directly from A to C. So in other words, taking shortcuts does not hurt. So if you were to go through a sequence of vertices and starting from A and then ending at B, well, you could go directly from A to B and that would cost you less. This is a consequence of the triangular inequality. Of course, in many situations, real life situations, we see that the triangular inequality holds. And this version of the traveling salesman problem is also very interesting. Of course, it is a special case of the general version of the traveling salesman problem, and we also see that this restricted version is NP complete. So the general version is NP complete and the restricted version is NP complete. Let's talk about the third restriction we looked at. That was called the Euclidean traveling salesman problem. The Euclidean traveling salesman problem, you're given n points on the plane, on the Euclidean plane, and now your job is to find the cheapest tour through all these vertices. So your job is to find the cheapest Hamiltonian cycle in this underlying complete graph. Of course, such an instance will also satisfy the triangular inequality, because we know the triangular inequality holds in the plane. If you go from point A to B and then go to C, well, going from A to C actually is cheaper. You know this fact that the sum of the two sides of any triangle is at least as big as the third side. Therefore, this particular restriction also gives us a metric version of the TSP problem, but this is even more restrictive, because on the Euclidean plane, the distance is defined by a certain formula that you know how to compute the distance between 2 points in the plane, and it satisfies many other constraints. The fact that everything is on a plane. This restricted version of the traveling salesman problem is also NP complete. Well, let me tell you another restricted version of the traveling salesman problem, and I will just describe it to you and you think about it for a moment. And that is, suppose that the endpoints are given to you in the plane and they are all in convex position. So this means that if you connect the points in a circular fashion, then you realize that what you get is a convex polygon. What about the traveling salesman in this case? If you think about it for a moment, you realize that when you put this restriction that not only the points have to be in the plane, but they have to be in convex position, the problem actually becomes trivial. The cheapest way is to go in a circular way and come back to the point where you started from. Therefore, if you add further restrictions, then the problem falls in the class P. And one way to deal with NP-complete problems is take a problem which is NP-complete and think of what are the natural restrictions you can put on the problem so that the problem actually falls in the class P. Sometimes this can be very fruitful, because what happens is the problems that we encounter in real life, the general version of it is NP-complete, but because these problems arise from real life, there are certain natural restrictions on these problems. And in the case that these natural restrictions bring the problem down into the class P, we can actually find a polynomial time algorithm. So how do we deal with hard problems? That's something that I want to talk about today, and then we will look at one particular example that I promised you in the last lecture. So the question that is staring us is, we have a problem that we would like to solve, and it happens to be NP-complete. Well, what do? We can try to search for a polynomial time algorithm, but it is unlikely that we'll find it. It is also unlikely that there exists one. So how do we go about this? We have a problem at hand and we need to solve it. Well, one way to attack this problem is to look at restricted versions of it. To restrict the problem, put further restrictions on it, and then see if the problem falls in the class P. So try to solve a slightly easier problem, a less general version of the problem than the one that you started with. And in case the restrictions that you're putting are actually natural and real life problems actually do have those restrictions for some reason, you're in business. You have an algorithm that you can use for practical problems. So that's one approach. Another approach to solve an NP-complete problem is you pick a problem, P, and you say, well, since the problem is NP-complete, I'm unlikely to find a polynomial time algorithm for it. In that case, what you do is you settle for an exponential time algorithm. So you think of an exponential time algorithm that takes, of course, a lot of time, and design the best possible exponential time algorithm for that problem. And then what you can do is you can actually work on what we call the exponent. You can try to make your algorithm so efficient and bring the exponent down that the practical problems that you want to solve can be solved on a large enough computer. Sometimes that can be done also, and sometimes it happens that the real instances that you find in real life are not too large. If that happens to be the case, in that case, you can afford to use an exponential time algorithm, provided it's not simply a brute force. There is a third approach that you can try on an NP-complete problem or on a hard problem. This approach is, well, not very popular with theoretical computer scientists, but actually has been extremely successful. And I would give you an example of it. This approach is that you start writing programs which solve these problems, and since the problem is NP-complete, these problems usually try to go through the entire search space. And then what you do is you use some sort of heuristic ideas to cut down on that search space. In some sense, you're using heuristics to actually solve practical instances that arise in common life. If you're able to do that, then the program that you have made, although it is an exponential time algorithm in the worst case, but for problems that arise in real life, it actually takes time which is not too large, and a computer actually gives you an answer. This approach is used, for example, in something called SAT solver. As we have looked at satisfiability, people have written very clever programs in which you can give them an explicit satisfiability question, and if the formula that you give them happens to be satisfiable, these programs will go through a very clever search and come up with an answer and with a satisfying assignment. And these programs can sometimes even deal with thousands of variables. So these are, strictly speaking, these are exponential time algorithms, but people are using these algorithms because they have clever heuristics embedded in them which cut down the search space and therefore end up solving these problems in reasonable time for problems that arise in practice. Well, the last approach to dealing with hard problems is what I really want to talk about today, and I want to give you an example of how it is done. This approach is called approximation algorithms, and we talked about it last time. An approximation algorithm gives up the idea that we're trying to find the best possible solution. On the other hand, it tries to find a good enough solution. So, for the traveling salesman problem, an approximation algorithm would be one that says, well, I'm going to take polynomial time, not too much time, but I will not find the cheapest tour. Instead, we will try to find a cheap enough tour. But the difference between an approximation algorithm and a heuristic is the following. In a heuristic, you have no guarantees. The solution that a heuristic will output will seem to be a cheap enough or a good enough solution. On the other hand, an approximation algorithm will give you a solution with a bona fide guarantee that this output, this solution that it is outputting, is this close to the optimal. So it will come with a bona fide mathematical guarantee that it is finding a cheap enough tour. We talked about approximation algorithms and how they behave for the traveling salesman problem in the last lecture. We noticed that, firstly, the general traveling salesman problem cannot be approximated to any degree, any constant degree of accuracy. So, for example, you cannot have a polynomial time algorithm. Of course, this is all under the hypothesis that p is not equal to np. You cannot have a polynomial time algorithm that would give you a tour which is, say, guaranteed to be 1,000 times the optimal tour. You can't even do that, and you can replace this 1,000 with any constant. And actually, if you look through the proof, you realize that you can replace this constant with any polynomial computable function. The second problem that we looked at was the metric TSP problem. For that, I told you that it is easy to design a two approximation algorithm, and that's what we will look at today. Furthermore, I told you that you can also design a 1.5 approximation algorithm. There is a very beautiful 1.5 approximation algorithm called Christophidis' heuristic, which is guaranteed to output a tour in a metric TSP instance of the problem, which is guaranteed to be within 50% of the optimal tour. So it is a 1.5 approximation algorithm. And then last problem we looked at was the Euclidean TSP problem, where the points are given to you on the plane, and there I told you that you can have an algorithm, a polynomial time algorithm, that can output a solution which is arbitrarily close to the optimal. So the ratio of the optimal versus this, the output of this algorithm is arbitrarily close to 1. So these three problems these three versions of the TSP problem, when we restricted them, they did not seem to change from the point of view of exact algorithms, but from the point of view of approximate algorithms, they behave very differently. One of them cannot be approximated, the other can be approximated to within 50%, and the third one can be approximated to within any degree of accuracy. So there's a whole spectrum that you get from this one problem. This is why the traveling salesman problem is such a favorite problem of computer science, because it has so many facets and it has so many versions which give us different things and show all the possibilities that can happen in the world of algorithms and complexity theory. So today's lecture is going to be concentrated on looking at a two approximation algorithm. And this would be hopefully the first example of an approximation algorithm that you would see, and we would also prove the approximation guarantee. And this would give you a flavor of approximation algorithms. After that, I would talk a bit about the PCP theorem, which is not the post-correspondence problem that we have studied before, but something different called the PCP theorem, the probabilistically checkable proofs theorem. That theorem deals with hardness of approximation, and it's considered to be one of the deepest facts or the deepest theorems in computer science. Let us begin today's lecture. We will start by reviewing the traveling salesman problem and then look at a two approximation algorithm for the metric TSP. The traveling salesman problem once again is the following, that a traveling salesman wants to start from his home and visit all the major cities in a district and come back to his hometown. Given that he has found out about the fares from each city to every other city, can we find the cheapest way for him to make his tour? So that is the basic problem statement of the traveling salesman problem. The metric TSP, the underlying graph is a complete graph, and the costs or the weights on the edges satisfy the triangular inequality. Let's review what the triangular inequality says. It says that the weight of A, C, cost of going from A to C is less than or equal to the cost of going from A to B and then going from B to C. Or the cost of going from A to C is less than or equal to the sum of the costs of going from A to B plus B to C. So the way you should think about it is, if you start from a point and you want to get to another point and you don't go directly but go through some other vertex in the graph, that would cost you at least as much as going directly. Thus, making shortcuts would not hurt you in this graph. The theorem that we proved last time was that the metric TSP is NP complete. And therefore, what we are trying to do is trying to come up with approximation algorithms for this problem. Now, let's think about approximation algorithms and why do we want them from a practical point of view? Well, since we know that finding a Hamiltonian cycle in this graph is going to take extremely large time, therefore, what we want to do is we find a cheap enough tour, but what we want to do is we want to do this in polynomial amount of time. Thus, we restrict our time, so we put a restriction on how much time the algorithm is supposed to take, which is restricted to be polynomial, and we allow the algorithm to relax its output. Exact algorithm will be required to output the cheapest tour in this graph. On the other hand, an approximation algorithm is required to take polynomial time, but it's allowed to not output the cheapest, but only a cheap enough tour. And then we will prove how good the approximate solution is for this algorithm. So let us review what an approximation algorithm is. We would want to review what an approximation algorithm is because when we design the algorithm, we'll keep in mind because we'll have to analyze our algorithm. This analysis is going to be very different from the previous analysis of algorithms that you have done. Previously, what you do is you design an algorithm like a sorting algorithm and you calculate its computational complexity. You calculate what is the amount of time or space it takes. But you never really look at its output and measure it. In an approximation algorithm, we have another task to do. So let us review what an approximation guarantee is for an approximation algorithm. Suppose the G is a graph with the cheapest tour of size t. If an algorithm guarantees to return a tour of size alpha t, then we say A is an alpha approximation algorithm. This two approximation algorithm will return an answer that is at most twice the cheapest tour. Similarly, a 1.5 approximation algorithm will output a tour that is 1.5 times t, the cost of the cheapest tour in this graph. If we have a 1.01 approximation algorithm, that would output a tour whose cost is at most t times 1.01. So what we are doing is we are going to design a two approximation algorithm for this problem. So our goal is to prove the following theorem, there's a two approximation algorithm for the metric TSP problem. So this would be the first instance of an approximation algorithm that we would design. Let me first simply explain to you the algorithm. The algorithm is made out of algorithms that you've previously studied. It uses those algorithms as subroutines. So what you've done is you're given a graph which satisfies the triangular inequality. The first thing we will do is compute the minimum spanning tree in this graph. So what we want to do is find the minimum spanning tree in this graph, and there is a polynomial time algorithm that would do that for you. You can use either Kershkal's or Prim's algorithm. Both those algorithms are not only polynomial time, but actually run really fast, and they have fast implementations. So you forget about finding a Hamiltonian cycle in your graph, but instead find a minimum spanning tree. So that's the first step of the algorithm. Now you take this minimum spanning tree and you tour all the vertices of this minimum spanning tree, starting say from any root, in a depth first search manner. And as you visit all the vertices, you start writing them down. The depth first search will start from the root, it will visit the whole tree and eventually come back to where it started from. If you look at this tour will contain all the vertices in the graph. So this tour will start from the root, visit all the vertices and come back to where it started from. So this seems like a nice way to tour the graph. Heuristically thinking, this also seems like a reasonably cheap way to tour the graph, because the minimum spanning tree is the cheapest possible way you can connect this graph, right? So if you go along this tree and visit all the vertices, that seems like a reasonably cheap way of touring all the vertices in the graph. Now, the only problem with touring this way in the graph is that you will end up visiting one vertex more than once. So for example, there will be vertices that you'll visit more than once, and so it would not be a Hamiltonian cycle in your graph. Well, now you do the simplest possible thing that you can think of. What you do is, every time you see a duplicate in this tour, a vertex that you've already visited, you just throw them out. So whatever is left over would be a Hamiltonian cycle in this graph. So this is our algorithm. So our approximation algorithm has three main steps. First is to compute the minimum spanning tree. The second is to tour the minimum spanning tree in a depth first search fashion. And the third one is to remove all the duplicates or to find a Hamiltonian cycle. The output of this algorithm is the Hamiltonian cycle that it finds. The first thing to notice is that this algorithm runs in polynomial time. And why is that? Because minimum spanning tree can be found in polynomial time. Depth first search takes for polynomial time, in fact linear time, and removing duplicates is not difficult and can be done in polynomial time. So this is a polynomial time algorithm. So we have satisfied the first requirement. The second thing to notice is that this algorithm does output a Hamiltonian cycle. Why is that? First of all, we compute the minimum spanning tree. It's a spanning tree, and therefore the spanning tree has all the vertices in the graph. Therefore, it starts with all the vertices in the graph. Then what we do is we visit all the vertices. Once again, the word all is very important. All the vertices in a DFS order. We use DFS to visit all the vertices. And DFS will start from a vertex, go through all the vertices and come back to where it started from. Therefore, we'll have a tour, a way of going through all the vertices of this graph. Then we remove duplicates. Thus, what we output is a tour in which every vertex appears exactly once. But that's the very definition of a Hamiltonian cycle. Therefore, this algorithm outputs a Hamiltonian cycle. So the first thing is, it is a polynomial time algorithm. The second thing is it does output a Hamiltonian cycle. Now the critical part. This is the part where we will do analysis, which is only done for approximation algorithms. What we want to do is we want to compare how good is the Hamiltonian cycle outputted by this algorithm with the cheapest possible tour in this graph. If you actually think about it, what we're doing seems to be a bit strange. Think about it. We have a graph and we use this algorithm to find a tour in it, a Hamiltonian cycle in it. And why did we just find a Hamiltonian cycle in it, not the cheapest one? Is because somehow it's very difficult to find the cheapest Hamiltonian cycle. How can we compare the output of this algorithm to something that exists inside the graph which we cannot find? So this seems like a contradictory thing that we are about to embark on. We want to compare the output of this algorithm with something, the cheapest tour in the graph, which we are not able to find. How do we compare this? Well, the idea is that we are not going to find that tour, but we are going to relate the properties of these two objects and therefore come up with our approximation guarantee. It's an ingenious way of arguing. It's an ingenious way of analyzing approximation algorithms. Let's continue. The first thing that we want to do is to prove the following simple fact. This fact says that the cost of the minimum spanning tree is less than or equal to the cost of the cheapest Hamiltonian cycle in the graph. So what we're saying is, if you take any weighted graph, which is connected of course, and you look at the minimum spanning tree in this graph, its cost would be cheaper than the cheapest possible Hamiltonian cycle that you would find in this graph. So in some sense, we are proving a mathematical theorem that the cheapest minimum spanning tree is always costs less than the cheapest Hamiltonian cycle in the graph. How would we go about proving it? Well, let's look at the proof. The proof says take the cheapest tour in your graph and delete any edge from this tour. So take a Hamiltonian cycle and delete any edge you feel like from this cycle, and what you have left over is a path. This path has all the vertices in the graph, and therefore this path is also a spanning tree. It's a very special kind of a spanning tree. Remember that tree is a acyclic graph, so a path doesn't have cycle and it contains all the vertices, and therefore it's a very special kind of a spanning tree. Since this path is a spanning tree, therefore its cost must not exceed the cost of the minimum spanning tree, because the minimum spanning tree by definition is the cheapest possible tree in this graph. Thus the cost of this path is at least as much as the cost of the minimum spanning tree. And of course, the cost of the Hamiltonian cycle is at least as much as the cost of this path, because we actually deleted one edge from the Hamiltonian cycle. The only thing that we require in proving this statement is that all the edge weights are positive. We have not yet used the fact that our graph satisfies the triangular inequality. So we have a very simple statement which says that the cheapest minimum spanning tree is always cheaper than the cheapest Hamiltonian cycle in any graph, as long as the weights of the edges or the costs are non-negative. That's the first observation. Well, think about this observation. This observation actually allows us to think of the algorithm and see why it makes sense. We picked a minimum spanning tree. Now we know that the minimum spanning tree is not going to be more expensive than the Hamiltonian cycle that we are looking for. So thus the first structure that we have picked is cheap and cheaper than the structure that we are ultimately looking for. Furthermore, what we have been able to do is we've been able to compare the cost of this minimum spanning tree with the cost of the cheapest Hamiltonian cycle, something that we don't know how to find, but something that we would like to find, or we would like to find something that is close to it. Thus, this algorithm makes a lot of sense. Now, let's look at the next step. The second thing now that we observe is that in any undirected graph, the cost of the tour given by DFS is 2 times the cost of this tree. So, take any undirected graph which has weights on its edges and take any tree that you want, any tree which is a subgraph of this graph that you have taken. So, you have an undirected graph and you're taking a tree, a spanning tree of this graph. And now what you do is you perform a DFS and tour all the vertices in this graph. The claim is the cost of doing that tour would be exactly equal to twice the cost of the tree that you took. Well, why is the case? Let's look at it through this figure. If we look at the following picture, here we have a tree which has come from this graph, and what we have done is duplicated every edge, and the arrows show how DFS proceeds and goes through this tree starting from the root, and then it comes back to the root. If you look at this, you realize that the DFS actually traverses every edge exactly twice. Since every edge of the tree is traversed exactly twice, therefore the cost of this tour is going to be twice the cost of the tree that you take. So now in our algorithm, what do? Well, we start with the minimum spanning tree, and then we use DFS to traverse this tree. So what is going to be the cost of this tour? Well, from this theorem or this fact, we realize that the cost of this tour is going to be exactly twice the cost of the tree. Now we chose the minimum spanning tree. By fact 1, the cost of the minimum spanning tree is at most the cost of the best or cheapest Hamiltonian cycle in this graph. Therefore, when DFS returns us the tour, it's going to cost at most twice the cost of the cheapest Hamiltonian tour. So the tour returned by DFS is not going to be more than twice the cost of the cheapest possible Hamiltonian tour in this graph. This statement is fairly spectacular if you think about it. We have been able to relate the cost of the tour of the DFS, which is being computed by this algorithm, with something that we wished we could find. But we have not found it, and yet we can make a comparative statement about it. Well, now what about the last step? What was the problem with the tour that was returned by DFS? The tour that is returned by DFS, let's have a look at it again. If you look at this picture, you realize that many vertices are duplicated. Some vertices are visited even more than 2 times. Therefore, this is not a Hamiltonian cycle in the graph. And our problem is to return the cheapest possible Hamiltonian cycle. So how do we convert this tour that goes through all the vertices, and some vertices more than once, to tour that visits each vertex exactly once? Well, we do the simplest possible thing. We shortcut, or we delete every vertex that we have visited before. Let's look at how we would shortcut this tour in this picture. Here is a picture for you in which we have a tour, which we have a tree, and then we have applied DFS to the tree, which visits all the vertices and many vertices more than once. And then after this, we've shortcutted this tour so that each vertex is visited exactly once. Well, the point is, if our graph satisfies the triangular inequality, then shortcutting does not increase its cost. Thus, the new Hamiltonian cycle that we output is not going to have cost more than the one that was outputted by the DFS. So, it's going to be a Hamiltonian cycle, and therefore, it's going to cost at most twice the cheapest Hamiltonian cycle in this graph. Let's talk about shortcutting a bit. Let's elaborate on it a bit. what we want to do is we want to say what happens when we shortcut. Well, when we're shortcutting, what we have is we start from a vertex v1 and we go to v2, v3, v4, v5 and eventually reach a vertex vk. A shortcut is you go straight from v1 to vk. So in shortcutting, we replace a part of the path which is v1, v2 up to vk by the edge v1, vk. Because of the triangular inequality, the shortcutting does not increase the cost of going from v1 to vk directly. What we note is, as a consequence of the triangular inequality, the weight of the edge v1, vk is going to be less than or equal to the sum of the weights of the edges that we find along the path that has been given here, namely the weight from v1 to v2 added to the weight from v2 to v3 added to the weight from v3 to v4 and so on all the way up to the weight from vk minus 1 to vk. In a graph that satisfies triangular inequality, shortcutting does not hurt. Therefore, this algorithm remains a true approximation algorithm. It's worthwhile to stop here and think about what would happen if we were to apply this algorithm to a general graph. Why can't we prove an approximation guarantee? Well, the first fact is true. If you look at any minimum spanning tree in any graph, its cost is going to be less than or equal to the cheapest Hamiltonian cycle in the graph. The second thing is also true. If you visit this minimum spanning tree using a DFS, the cost is going to be at most twice the cost of the Hamiltonian cycle. However, when you try to shortcut, two things can go wrong. Firstly, if you're talking about a general graph, if there is an edge from A to B and then B to C, there may not be an edge from A to C. In other words, the graph may not even have a Hamiltonian cycle. So what we can do is we can say, well, let's even assume that the underlying graph that we're working on is a complete graph. Well, in that case also, when you shortcut, when you go from A to B and then B to C, instead you take the edge directly from A to C, its cost can just go up. So the output that you would find is going to be extremely different. It can blow up by as much as you want. One can make examples where it blows up arbitrarily large. Thus, this does not give you an approximation algorithm for the general TSP problem. But because the metric TSP problem satisfies this very nice inequality, therefore it does give you a two approximation algorithm. Let's now have a fresh look at our algorithm and do the analysis along with the algorithm. The algorithm takes as input a complete graph and weights that satisfy triangular inequality. The first thing we do is we compute the minimum spanning tree T of this graph. And here we have a guarantee that the cost of this tree is less than or equal to opt. Opt is the optimal cost of the Hamiltonian cycle in this graph, the cheapest tour. Then the second step is we tour the tree using DFS and output all the vertices encountered on this tour. This doubles the cost of the tour. The cost of our tour, and this tour has repeats, is less than or equal to 2 times the cost of the minimum spanning tree and therefore less than or equal to 2 times the opt, the cheapest Hamiltonian cycle in this graph. And lastly, we output all the vertices after removing duplicates. And this cannot increase the cost. Therefore, the cost of what we output is less than or equal to 2 times the optimal. What we have seen now is a two approximation algorithm for the metric TSP problem. It was an extremely interesting algorithm. The analysis of the algorithm was in many parts. First of all, we established that the algorithm was actually a polynomial time algorithm. Then we established the fact that the algorithm outputs what it's supposed to output, namely a Hamiltonian cycle in this complete graph. After that, there was this analysis which is very unique to approximation algorithms, where we compare the output of this algorithm with the best possible or the optimal possible algorithm, or the output of the exact algorithm if there were one. or an exponential time exact algorithm. And we show that this algorithm outputs something which is no larger than twice the optimal possible tour. In approximation algorithms, improving the approximation guarantees is a big challenge. So now you have seen a two approximation algorithm for the minimum spanning tree problem. And one very challenging problem for you is, if you want to take up this challenge, is think of a better approximation algorithm for the metric TSP problem. Well, I won't keep the suspense and I'll let you know that yes, there is a better approximation algorithm. In fact, there's a 1.5 approximation algorithm for the metric TSP problem. That algorithm is extremely ingenious and extremely clever. However, improving this 1.5 to something smaller, let's say 1.499, is a big open problem in computer science. It's a very old problem, it's a very exciting problem, and if somebody were to make any headway towards finding a better approximation algorithm for metric TSP problem, that would be very exciting for the computer science community. Now what I want to do is talk a bit more about approximation algorithms and hard problems. Remember, we developed the theory of NP-completeness in order to show that problems are hard. What we wanted to do was to prove that problems are hard, but unfortunately we were not able to do that. So what we did was we developed this theory of NP-completeness, which gives us huge evidence that problems are hard. The theory of NP-completeness tells us that if you find a polynomial time algorithm for a given NP-complete problem, well, you would have solved all NP-complete problems in the sense that you would have found a polynomial time algorithm for each single problem in NP. And therefore, this indicates that these problems are extremely general and may not be solvable in polynomial time. Well, once a problem is not established to be NP-complete, then what do? We stop looking for polynomial time algorithms for this problem and instead follow other approaches. One approach is to look at restricted versions of this problem. Another approach is to actually start designing approximation algorithms. So, for example, for the TSP, we looked at an example of an approximation algorithm. So what people do is they look at an NP-complete problem and they think up of clever approximation algorithms for this NP-complete problem. So for the TSP, we were able to find a two approximation algorithm. And then, well, somebody can come and say, can you do better? And the answer is yes, you can find a 1.5 approximation algorithm. And then somebody can ask whether we can still do better, and so on and so forth. Well, this is one way we can try to keep improving the approximation guarantee. The question is, how would we know, or how would we ever find out whether we've found the ultimate approximation algorithm for that problem? Finding the ultimate approximation algorithm would be a wonderful thing, and knowing that this is the ultimate approximation algorithm would be great, because then we can even stop our search right there. We'll stop looking for further improvements on our algorithms. So for example, the question whether 1.5 approximation algorithm for the metric TSP problem is the best that can be done or not is an extremely intriguing question. How do we answer questions like that? Well, once again, in computer science, we have algorithms and we keep improving them, and then we try to develop a theory of hardness. So, for example, we were designing polynomial time algorithms and we developed the theory of NP-completeness, which was the theory of hardness. The question is, can we make such a theory for approximation algorithms? Is there hardness of approximation? Can we prove hardness of approximation? Can we prove that some problems are so difficult that they cannot even be approximated properly? What are the limits? These are extremely intriguing questions. We have looked at one little theorem. We looked at one theorem which said that the general TSP problem cannot be approximated to any degree of accuracy. So you cannot have a C approximation algorithm for the general TSP problem for any positive C. Well, what about other problems? Is there a unified theory like the theory of NP completeness for hardness of approximations? Well, this is where computer science gets really exciting. In the 1990s, several computer scientists took active interest in approximation algorithms. Usually, it is not difficult to show that problems are NP complete. However, it is very difficult to show that approximation algorithms for problems may not exist, or polynomial time approximation algorithms for problems may not exist. This investigation led to one of the deepest theorems in computer science, which is now called the PCP theorem. Here, PCP stands for probabilistically checkable proofs. The PCP theorem provided us with a unified theory of hardness of approximation. Using the PCP theorem, it is possible to prove that if there are good enough approximation algorithms for certain NP-complete problems, then P would be equal to NP. Thus, the PCP theorem plays the same role for approximation algorithms as the Cook-Levin theorem played for the theory of NP-completeness. However, the PCP theorem is much more sophisticated and it's extremely deep. The proofs of the PCP theorem are not very simple. The original proofs used some very algebraic techniques. However, now people have found purely combinatorial proofs of the PCP theorem. Well, in this course, we will not say too much about the PCP theorem, but let me explain to you what the theorem says, and it's quite spectacular. Well, let's think about satisfiability. Suppose I have a formula phi which is satisfiable. Well, we know that satisfiability is in the class NP, so it's very easy for me, once I've found a proof, to present you with that proof. And what you can do is you can check the proof of correctness that this formula is satisfiable. Usually, what is the proof? Well, I claim that a formula phi is satisfiable, and the way I prove it to you is that I give you a satisfying assignment for the formula. To check the proof, you substitute the satisfying assignment for the variables, and you do some small computation, a polynomial time computation, and you see if the formula is satisfied. If it is, you accept the proof. So, for every problem in NP, for example, the satisfiability problem, if phi is satisfiable, there is a very short or easily checkable proof which proves that the formula is satisfiable. Now, the PCP theorem says more. Now, let's imagine that I want to prove to someone that a formula phi is satisfiable, but my task is to give them such a proof so that it becomes extremely easy, extremely trivial for them to check my proof. This, what I want to do is give them a very transparent proof, a proof that is so easy to check that they don't have to put any or too much effort in checking whether the proof is correct or not. So, P theorem says that for satisfiability, you can find such transparent proofs. Well, what do we mean that these proofs are very transparent? Someone who is lazy and who would like to check the correctness of this proof will have to only do the following. They will have to pick 3 random bits of this proof and check those 3 random bits, and once they look at those 3 random bits, they will be convinced with high probability, with probability at least half, that the proof is correct. So in other words, this proof would be so transparent that in order for somebody to be convinced that the proof is correct, they will have to only generate 3 random bits and look at 3 random bits of this proof. And once they have examined 3 random bits of this proof, they will be able to say with reasonable certainty that the proof is indeed correct. The existence of such transparent proof is far from being clear at all. The existence is just highly spectacular that one can actually come up with these proofs which are so transparent. Once we have the PCP theorem, then people can use this PCP theorem to prove that certain problems are hard to approximate. In some cases, this whole idea has been so fruitful that we know approximation algorithms, and the PCP theorem proves to us that improving these approximation algorithms will amount to showing that P is equal to NP. The PCP theorem is an extremely deep theorem in computer science, and I would urge you to look it up and read about it, and possibly at some point read its proof, because it's completely fascinating. Well, in the next lecture, we're going to move away from approximation algorithms and time complexity and talk about space complexity. I'll see you next time. Thank you and goodbye.